So, how to choose the correct analysis method for the beam analysis? Today we are going to see the how to classify the shallow beam and deep beam, and the assumption or background behind the Euler Bernoulli beam theory and Timoshenko beam theories, and by understanding all these things, so how to choose the correct analysis method for the various type of beams. Let us assume a beam like this, where the clear span is called L and the total depth is called D. That beam subjected to uniformly distributed load of Q kilonewton per meter, and we all know that deflection due to this loading for this simply supported span is 5 WL power 4 by 384 EI, where E is the Young's modulus of the material and I denotes the moment of inertia of the cross section. In addition to this, there will be additional one component, which is the deformation due to shear force. Usually we used to neglect this. Basically this will be very less in case of a shallow beam, but in case of a deep beam this shear component will be high. So we cannot simply neglect this, and we cannot proceed this. So that we will see by result. What we are seeing here is the deflection diagram for the various L by D ratio of the beams. So 1.5, which here 2, 2.5, 3, here it's 8. So the deflection between two theories, one is Euler Bernoulli beam theory, another one is Timoshenko beam theory. If you see here, when the ratio is less, this Timoshenko beam theory gives more deformation because it considers the both flexural and shear deformation, whereas Euler Bernoulli beam theory having less deflection because it considers only flexural deformation. But in the same case, if we move on like this, if the spans are more, there is no much difference between the two theories, which means when the span is very less, not only the flexure, shear having more impact in the deflection and the force, everything. So we cannot simply neglect this. And if the spans are more, so we can neglect those things. So what is the concept behind these two theories? The assumption is, the main important assumption for the bending theories are the material should be homogeneous, isotropic, and plane section cross section is plane before bending and remains plane after bending, which means homogeneous means the particle, if you take any particle either here, this location or this location or this location, if you take anywhere, that physical property of the particles will be uniform throughout the span, that is called isotropic. Sorry, homogeneous. What is isotropic? Isotropic means irrespective of the direction, force applied in any direction, the physical property, this behavior will be same. That is the meaning of isotropic. Same, that is common for both theories, Euler Bernoulli beam theory as well as Timoshenko beam theories. The difference is the cross section. If you see here, the vertical line here, this is before bending. Once load is applied after bending, this is the deformed plane. So this is called a neutral axis, where there is no strain, that is called a neutral axis. When compressive strain means it is compression zone, and tension strain is called tension zone. So this cross section is plane even after bending. Not only that, and that plane is always perpendicular to the 90-degree to the neutral axis. If you see any here, or here, everywhere it will be always 90-degree. So slope of this deformed plane is there, right? That is called curvature. So this is called radius of this curve. So that 1 by curvature is equal to represent the radius of this bending. So in Timoshenko beam theory, so this cross section plane before bending and remains plane after bending is valid, but this not only the deformation due to flexure, it also consider the uniform deformation throughout the section due to shear as well. So because of this, that another assumption, this plane is always perpendicular to neutral axis is not valid here. This will be plus or minus some value, so this not, it will not maintain 90 degree here based on the shear component. So there is no shear, it will maintain 90 degree. If there is a shear component, this will not maintain 90 degree, it will have some 90 plus or 90 minus. So that is the main difference between the Timoshenko beam theory and general beam theory or Euler Bernoulli beam theories. So in summary, so how to classify the beam, whether it is a shallow beam or deep beam. So if you see here, here and all we can see there are considerable amount of shear contribution because there is a huge difference between the two theories. So when there is a considerable difference by the shear component, then we should call it as a deep beam, otherwise shallow beam. So it's all depends upon the code. In Indian code says that if L by D is less than 2, then it is a deep beam, or some code says L by D is 2.5, some code says L by D equal to up to 4, it is a deep beam. So but by seeing this, if there is, these are all shallow beam, there is no difference, there the shear component is very negligible, so we can call it as a deep beam. Otherwise we can consider all these three as a deep beam, so these are all shallow beam. So this is how we should classify the beam, whether it is a shallow beam or deep beam. And when we should use the this is the stiffness matrix of the Euler Bernoulli beam theory, so which is applicable for only shallow beams. If in case of deep beam, that too not all the deep beams, when there is a plane cross section is remains plane even after bending, but it is not maintaining the 90 degree with the neutral axis, those cases we can go with Timoshenko beam theory. So Timoshenko beam theory stiffness matrix will be look similar to this. So wherever this pi is the component there, right, that pi component will take care of the additional deformation due to the shear. If at all we are not able to judge whether it is within the limit of Timoshenko beam theory or elastic beam theory, better always go with this finite element analysis. So it will take care of all the things, or maybe if it is a deep beam, the ratio is somewhere here, directly we can go for sudden time method for the more accurate analysis. So anyway, we cannot use the Euler Bernoulli beam theories.